Okay, so I've had several emails on isomerizable double bonds and what exactly that means, how to tell. And I've tried to respond by email. There's another tutorial that I uploaded last year that you could watch that might... Anyway, if you've watched that and you haven't gotten it, I thought I would do another one here on Sunday morning. And this really will get to it. So there are 4 carbon-carbon double bonds in this molecule. I'm going to ask you to hit pause, take a look at this molecule, go away and try to come up with which ones you think are isomerizable and which ones aren't. So hit pause, go do that. Okay, are you back? First of all, I've already done this for 2 of them. I've put the hydrogens in. I think a lot of times you guys, you're still getting used to the line structures, and so a lot of times you guys aren't really figuring out exactly what's on the carbon. So I initially put in 2 of the hydrogens. Go ahead and do the rest. Hit pause, do that. I'm going to do it here. All right, so there's an H there. These are methyls. Again, a line that just ends like that, a bond that just ends, that's a methyl group. So this is a CH3, as is this, a CH3. Okay. That carbon now has 4 bonds. 1, 2, 3, 4. This carbon has 4 bonds. 1, 2, 3, 4. Okay, so this carbon has 1, 2, 3 bonds shown. The other is there. And again, any carbon in a carbon-carbon double bond or a carbon-oxygen double bond or a carbon-nitrogen double bond is sp2 hybridized trigonal planar, right? So this atom, I'll put a little star by it just for now. That star there, that atom is flat, right? The H is sticking up in the plane of the board. The next carbon is in the plane of the board. This carbon's in the plane of the board. Okay, same thing here. There's H is there. And if you want to, if it makes you feel better, if it helps you to understand at this point, like I said, there's no shame in just now being and still getting used to this line structure. Go ahead and put all the H's in if you want. Just make sure you do it right and make sure you say an H, right? If you just draw lines there, that's 2 methyl groups. So you've got H's there. Okay, so now you're probably wondering, I asked you to go away and identify the isomerizable double bonds. So I'm going to circle the double bonds that are isomerizable. Just those 2. Okay, so that's the answer. If you got it right and you think you understand it, that's fine. You can hit stop. I'm going to walk through then. This will take a little bit of time, so the video is a little longer, but I'm going to walk through why the 2 double bonds that aren't isomerizable aren't and why the 2 that are. I'm also going to erase some of the extraneous bits. No, I need that one, don't I? Okay. Okay, so formally an isomerizable bond can't talk and write. Make sure I'm still on the screen and in focus. Yeah. So formally, an isomerizable double bond is one that can be either cis or trans and isn't constrained to one or the other. Okay, so let's walk through that. I'm going to ask you again to hit pause and decide if the double bonds shown are cis or trans, also E or Z. So a double bond can be E or Z without being cis and trans. But I want you to figure out cis, trans, EZ for all 4 double bonds. Okay, hit pause, do that. I'm going to take a sip of tea, let you come back. Okay, so let's start on the left. So what you do to determine E or Z, look at carbon 1. Well, I'm just going to work left to right. So let's take this first carbon and then assign priorities to the 2 groups on it. All right, 2 of the bonds to that carbon are taken up in the double bond. Don't consider that for the moment. Just consider the 2 other groups. And then this goes like the Conning-Ingold prelog that we talked about in class. This goes by atomic weight. So you've got carbon versus hydrogen. Again, you go until you see a difference. So this is going to be 1 and this is going to be 2. All right, you don't have to do anything else at this point. Go to the other carbon on the double bond and do the same thing. Carbon, hydrogen, 1, 2. Okay? If the ones are on the same side, right? These two ones are on the same side of the double bond. That is a Z double bond. Okay? Z is also, in this case, because two of the substituents are identical, so the two groups are both H. So identical groups, cis equals cis, trans equals trans. Okay, so this is where you can get E and Z not being cis or trans. If this H were, say, I don't know, methyl, then this would still be a Z double bond, but you couldn't say it's cis. It's down in the weeds a little bit, but it's something you do need to know. So this double bond is formally a Z double bond. If you have trouble remembering E and Z, cis and trans, this is corny, and you have to sort of put a German on it. So Z, Z if you're not American, but Z equals cis, zis. You could shorten this to zis double bond. Put like a Russian, German gangster accent on it, and you get cis and Z. Okay, even if that doesn't make sense to you, hearing me do it, maybe that'll stick in your mind. So then that means the other one is trans. Okay, so first double bond is Z. Let's move on to the second double bond. I'll do this in a different color. Okay, so again, take this carbon, do 1 and 2. Well, carbon, carbon. All right, that's a tie. You've seen this in doing absolute configuration. What is that? But they're different. They're clearly different, right? CH2, CH, different. So this one is bonded to CH and H. This one, because of the double bond, is bonded to CC and H. C beats H, so this side is 1, this side is 2. Okay? Go to the next carbon in the double bond, carbon versus hydrogen. Again, 1 and 2. And so once again, you've got the ones on the same side. That's a Z double bond. Okay, do the next one. Okay, oh, but back to this middle one. It's a Z double bond, but it is not cis or trans. CH2, look at the 4 groups. You got 4 different groups on it. CH2, CH, sp2ch, in a ring, H, and sp2ch not in a ring. So 4 different groups. You can't say if it's cis or trans. You can say it's Z. This is where you have to use E and Z. E and Z reflect the isomerization state of a double bond outside of cis and trans. Okay, so we go to the next double bond. And I'm going to go to green with this one. Okay, so first carbon here, carbon, hydrogen. Carbon is 1, hydrogen is 2. The next double bond, hydrogen and carbon, carbon's 1, hydrogen is 2. And now the 1 groups are on opposite sides of the double bond. So this is an E double bond. And because 2 of the groups are identical, the 2 H's are trans to one another, you can say not only is it E, but it is formally a trans double bond. Okay, let's do the last one. I'll indicate the 1s and 2s in black for this one. So first carbon in the double bond, H and C. H is 1, carbon is 1, H is 2. Let's go to the second carbon in the double bond, methyl and methyl. Carbon, formally, carbon-carbon ties, right? Carbon ties. That carbon is bonded to 3 H's. This carbon is bonded to 3 H's. And you've run out of molecule, okay? Once they're the same and you've run out of molecule, they're the same. So these are identical groups. That means this double bond is neither E nor Z. Which means that's the first test. If a double bond can be neither E nor Z, it's not isomerizable. So this one I did not circle initially. Remember, this red circle means it's an isomerizable double bond. This last double bond on the right, 2 identical groups on 1 carbon. So that's the test. Look at each carbon individually in a double bond. Do they have identical groups on them? This time they do, right? Methyl and methyl. 2 identical groups on the same carbon. It doesn't matter which way you twist that, so it's not isomerizable. Okay, the 2 double bonds here in the middle, the double bond, the internal double bond on the right is E, the one on the left is Z. So these are E and Z, they're isomerizable. And there's no constraint then. The next one is, so they can be either cis or trans, and there isn't a constraint, right? I could flip that over and I don't have to change the bonding anywhere else. I could flip that one and I don't have to change the bonding anywhere else. I'm going to talk here in just a second about actually flipping the bonding. So this will be a relatively long tutorial. Feel free to drop out anytime you know what's going on. The last double bond, the first one on the double bond on the left, is Z. Okay, so it can be cis or trans. So it meets the first criterion to be isomerizable. It's Z, and it could be E. You can imagine twisting that around. But this ring constrains the double bond. Okay, so if I were to break the pi bond, rotate around that, I basically have to pull all these molecules as well, because this is a ring. I have to pull these molecules over to the other side. And so what would happen then, this carbon would be here, and the chain would have to wrap back around to this side of the double bond in the space of only 1, 2, 3, 4 carbons. Okay, and it just can't do it. You can't have a cis double bond in a 6-membered ring and meet the other structural requirements of the atoms, right? They're sp3, they want to have a bond angle of 109.5. So this double bond is constrained. So it is not isomerizable. So basically, to sum up, looking for an isomerizable double bond, you're looking for a double bond that can be E and Z, which means it has 2 different groups on each of the sp2 carbons, and that's not in a ring. There are some other, that's what you should learn now. There are constraints that can occur, which we haven't talked about and probably won't in this class. And in fact, if your ring is big enough, you can have a trans double bond in it. That really starts at 8. By 9, 10-membered rings, the double bond can be cis or trans either way. But don't worry about that. Really, right now, double bond in a ring, not isomerizable. Double bond that can't be E or Z, not isomerizable. So then one last question here. How many stereoisomers could you have for this molecule? I'm going to erase this now, so remember, you can pause, rewind, rewatch. I'm going to ask 2 questions and ask you to answer them. So how many stereoisomers can this molecule have? And how many of those stereoisomers are diastereomers? Hit pause, think about this, try to answer those 2 questions. Alrighty, hope you did that. So first of all, we have 2 isomerizable double bonds. How many chiral centers do we have? We don't have any, right? None of the sp2 carbons can be chiral. Remember, sp2 cannot be chiral. Okay, because they're trigonal planar. They have a plane of symmetry by definition through the plane, through that plane. CH2, 2 H's, CH2, 2 H's, CH2, 2 H's, CH3, 3 H's, CH3, 3 H's. A methyl can never be chiral. So, 0 chiral atoms. So the formula then is 2 to the 2, formally 2 plus 0. So that's going to be 4 stereoisomers. Okay? We can't isomerize here, we can't isomerize there. This one can be E or Z. That one can be E or Z. So we have two independent double bonds. We could have EE. We can list these out. So we could have EE. We could have EZ. We could have ZE. And we could have ZZ. You see where this formula comes from when you just do it with 4. Okay, the one we actually have is ZE. So this is the one that's up there above. Okay, so now the next question is, how many of the stereoisomers for this molecule are diastereomers? And the answer is all of them. All right, EZ isomers are always diastereomer. That might be misspelled. Okay, but there are no chiral centers in the molecule. The molecule is in fact not chiral. Okay, so you can't have an enantiomer. The only other kind of stereoisomer is a diastereomer. So if this particular molecule has 3 other diastereomers or 3 other stereoisomers, all 3 have to be diastereomers. Okay, I was going to put on a little bit at the end about why the double bond can't rotate. I'm just going to remind you, go back and look at the pi bond. There are tutorials, there's stuff in the book. Look at how you make a pi bond. Okay, there's not any free rotation about the carbon-carbon double bond at room temperature, even at really high temperature. So you can do this. There are chemical reactions where you can break the pi bond, have the molecule rotate, and then remake the pi bond to isomerize a double bond. But it's a chemical reaction. It takes a lot of energy. So you can't just do this. If we have this molecule in a bottle, it will just sit there. It won't isomerize. It's a very rigid molecule. So double bonds actually put a lot of rigidity into a molecule. I'm going to end it there. Rewatch this. I hope this makes some sense to you. And I hope you'll be able to identify isomerizable double bonds by Tuesday.